So the next talk will be by Jiaxuan Yu, who also just obtained a PhD from our research group here at Stanford. Jiaxuan will give a talk about graph neural networks and graph machine learning for financial networks and the framework he developed for analyzing this type of super high-speed dynamic throughput networks. Jiaxuan, the floor is yours.
Thanks, Yuri, for the introduction. My name is Jiaxuan. I'm from Stanford University. Today, I'm going to share some of my thoughts about graph learning in financial networks. This is a joint work with Tianyu, Fanyu, and Yuri. In this talk, I will focus on the concept of financial networks. A financial network is a general language that can describe financial entities and their relationships. Here, I show two examples. In the first example, I show international banking, where we can view different countries as different nodes and the capital flows among the countries as the edges. In another example, Bitcoin transactions, we can view this Bitcoin wallets as a node and the transactions between these wallets as the edges. Our goal here is to build a graph learning framework for financial networks. Such a framework can have a very wide applications. It can be used for, say, fraud detection, anti-money laundering, and anomaly detection. Specifically, our input to such a framework will be a financial networks. We'll use a graph neural network to process that neural network and make a variety of predictions, such as node level, subgraph level, and ledge level predictions. Specifically, we could ask a node level task, for example, which node is a fraudster. We could ask about edge level tasks that can tell us like which transactions are fraudulent or anomalous. Finally, we can do some subgraph level tasks where we want to detect those money laundering subnetworks. A great question to ask here is that why do we need graph representation here? Traditionally, people have been using transaction-based approach. For example, a transaction can tell us on January 3rd, client A sends company B $500. Based on this transaction information, people can build machine learning models and make predictions. The issue of this kind of approach is that it ignores the context of a transaction. Here, we propose to use graph-based approach, and we will represent those transactions as a dynamic graph, as I show in the right. Here, we have three types of nodes: client node, bank node, and company nodes, and they are making transactions with each other, which are represented by the edges. And based on this graph representation, we can make predictions based on the entire graph rather than just a single transaction. The benefits here is that we can represent a transaction which are much broader context. Besides, this kind of approach requires fewer engineering because the graph itself already serves as a good feature representation. Now I have introduced some basics about machine learning on financial networks. Next, I'm going to discuss our Roland framework that builds GNN for financial networks. In our Roland framework, our goal is to build GNN for financial networks. And this is based on two insights. First, we want to transform those financial networks as GNN computational graphs, and then we will train that GNN by learning from diverse signals. Specifically, we will take a financial network as the input, and then we will apply a small neural network to each of the edges, which is each of the transactions. The goal of this neural networks is to learn how the information is propagated among these transaction accounts so that they can learn how to make proper predictions on the financial networks. We will train this system using a variety of learning signals. For example, we can use some self-supervised learning signals. These are extracted from the raw graph input data. For example, we can ask, will there be a transaction? What is the transaction amount? And when the transaction will happen? Besides, we can also apply some supervised learning objectives. And these are from external sources beyond the graph. For example, we can predict if a given edge involved in a fraud activity or it is involved in a money laundering activity. A key research question in this Roland framework is that how do we apply static GNNs to these dynamic prediction settings? In the left, I show an example pipeline for state-of-art static GM. Here, the input will be a static graph, and we will process the input graph with several layers of graph neural network. These layers could be connected by some, say, skip connections to improve the performance. And within each GN layer, there are also a lot of complex designs. For example, we could apply a linear layer, batch norm layer, dropout layer, etc. After making this GN process, we'll finally output the predictions on this static graph. For example, we can predict if this given transaction is fraudulent or not. In real-world financial networks, however, the problem is the graph will be dynamic. So you can view a dynamic graph as a sequence of graph snapshots where different snapshots are different. The question here is that can we adapt a state-of-art static GN to these dynamic prediction tasks? Our solution here is based on a simple but really effective idea. Here, we want to recurrently update our node embeddings at each layer. To do so, we introduce a new module to a static GN. Here, we introduce a module called embedding update, whose input are the previous embeddings from the same layer computed from the previous snapshot, and current embeddings from the previous layer computed as a current snapshot. By combining these two inputs and making some neural net computation, we can output the update node embeddings. The benefit of this approach is that you can see it's pretty simple, but we also showed in the experiment that it's really effective. Besides, by doing so, we can benefit from the state-of-art designs that are happening from a static GN. Another challenge in Roland is how do we effectively train the system. Here we have two innovations, incremental training and meta-training. The reason we want to do incremental training is because real-world financial graphs are really large. They can often contain millions or even billions of nodes and edges. So we choose to only keep part of the graph inside the GPU to save the memory cost. In particular, we'll only keep the GN model, historical node states, and incoming new graph snapshots in our GPU memory. And by doing so, we can really be memory efficient, and we show it works well in practice. Another technique we've done is meta-training. Here, we'll train a meta-GN that can quickly adapt to new incoming data. The benefit of this meta-training is that this way, Roland does not have to be frequently retrained because it can quickly adapt to the new data. And I will show some analysis later. Now I have introduced our Roland framework. Next, I'm going to share some results and insights that we have learned from our Roland framework. We implement Roland with a GraphGym API. GraphGym offers a standardized pipeline for graph learning. This is proposed in our paper Design Space of Graph Neural Network. Now, GraphGym will officially become part of PyG 2.0. And in the next of the talk, I will talk more about GraphGym. GraphGym features a general GN design space, which allows users to pick the best design from an enormous design space. Besides, it features as a clean interface so that users can compare the best designs to choose for their specific applications. Here, we implement the financial prediction pipeline using GraphGym, and we have adopted many optimal design choices that we learned from GraphGym. And here's an example financial data set that we're considering. In our data set, the data set captures about transactions between companies from a bank clearing system. There are more than 300 million transactions, 6 million accounts, and 6 years of transaction data. Here, I show three different distributions about the transaction amount, the degree of a given account, and the history length of a given account. And you see that they roughly follows the power law distribution, which we often observe in real-world graphs. The first task we care about is to classify fraud transactions. Our setting is a supervised learning setting, where the labels are highly unbalanced because only 2% of all the transactions are fraudulent. We'll apply a random data set split where 80% of the data are training, 10% of validation, and 10% testing. We adopt the standard metric for binary classification, AUC, and here the random guess will have an AUC of 0.5, and higher is better. Here, the best non-deep learning baseline we have implemented only has an AUC about 0.8, whereas a simple GNN implementation using out-of-box PyG has an AUC of 0.81. With our Roland framework, we work much better and produce an AUC of 0.94. Our second task here is to forecast future transactions. The task setting is self-supervised or unsupervised learning. We adopt a rolling prediction setting where on each day, we will use all the historical information to predict the transactions on the next day. The metric we adopt here is mean reciprocal renting, or MRR, of ground truth future transactions. Here, we compare Roland with a bunch of state-of-art dynamic GNN baselines, and we show that Roland can significantly outperform them. Besides showing these figures and results, here we did more analysis on Roland's performance over time. In the first row, we show the transaction amount over time, and you can see that there are some spikes over the year. On the second row, we show the number of retraining epochs of Roland. And we can see that in most of the cases, there's no retraining needed. That is thanks to the meta-training perspective of Roland framework. And there are some small spikes in the middle, which means that the model is adapting to the pattern changes of the data. And in the final row, we show the performance of Roland measured in MRR and a record 1. And you see that Roland can maintain a pretty robust performance over transaction pattern changes. Another question we want to ask is that what kind of transactions does the Roland pay attention to? And this way, we can interpret Roland's predictions. Our method here is to inspect edge attention scores of the last GNN layer. Specifically, we will select edges with low and high attention scores, and we will get the feature value distribution of these edges. We found some very interesting observations. First, we find that Roland is paying higher attention to larger transaction amounts. Another interesting finding about transaction pattern is that Roland is focusing more on non-financial to household transaction and domestic to abroad transactions. So these are some of the insights we found based on the Roland's predictions. Having discussed Roland's result, finally I'll discuss one particular application of Roland on anomaly detection. Here, our goal is to detect anomalous transactions without external supervision, which mimics the real use cases because labels are usually scarce and costly to obtain. Our approach here is to combine our Roland framework with outlier detection models. To do so, we define a set of self-source objectives to train Roland. Specifically, we focus on some indicators and patterns of money laundering activities. For example, here, one such indicator is investment funds sent to countries of concern. And we'll translate that indicator into a GNN objective, for example, predicting the country of the sender. Similarly, we define other objectives for GNN to train our framework. By using that set of self-source learning objective plus outlier detection objective, we are able to repurpose a Roland for this anomaly detection task. Specifically, our task is to detect anomalous transactions without any supervision. And the goal is to simulate real-world anomaly detection use cases. In particular, we'll corrupt the dataset to see if Roland can extract those corruption behaviors. And we'll report the precision and recall of the corrupted edges detected by Roland. We define several ways of corrupting the dataset. For example, we can corrupt a transaction amount, for example, multiplying it by 100 times. We can corrupt the country of the transaction by randomly assigning a wrong country to the transaction. Or we can corrupt the recipient, where we rewire the transaction between normal receivers and senders into some wrong receivers and senders, and see if Roland can pick them out. In the experiment, we show that Roland can significantly outperform the baselines. For example, compared to rule-based baseline, our model can achieve more than 170 improvement in terms of precision recall. And compared to other deep learning baselines, Roland can achieve more than 14% precision recall performance gain. Finally, I show an interesting visualization of Roland of a subset of our transaction network. Here, the red dots are the potential anomalous accounts predicted by Roland, and the black dots are the normal accounts. So that's everything about my talk. To recap, I have talked about the Roland framework. We have shared some result insights that we learned from Roland, and we talk about the application of anomaly detection. For more resources, you can check out our paper and learn more about GN from our pig.org website. Thank you.
Opportunity for the audience to ask questions.
Thanks for the wonderful talk. You mentioned that you have used outlier detection in one of your previous slides. Mm-hmm. So what methods you have used in the outlier detection there?
Mm-hmm. Yeah, that's a great question. Here we use one class SVM objective detection, outlier detection objective, as is shown here. Yeah, and we find it performs pretty well when we combine it with those self-supervised learning objectives.
Thank you. Another question comes from the online. The question goes, you had a very unbalanced data set. Did you use any resampling techniques to somewhat rebalance the training examples that the GNN saw?
Mm-hmm. Yeah, that's also a great question. And that's true because the data set, since it's highly unbalanced, what we did is to sample the positive and negative samples so that they follow a similarly balanced data set. So indeed, we do some rebalance techniques here.
Thank you. Question at the back.
Yeah, I run a cyber risk management platform. My question is around, so are there any use cases for cyber security? Have you guys used your research for cyber security kind of use cases, anomaly detection?
Mm-hmm. Thanks for the question. I think the question is about can we repurpose our methods for cybersecurity? And I think the answer is yes. For example, if we can get this Bitcoin transaction network, and there are some, say, phishing activities or some malicious activities, I believe we can also repurpose our Roland framework for that use cases. So yes, I think the answer is yes.
Yeah. And I will just add, we also have work done on phishing detection, on email, and some other applications. Happy to chat more offline. And then the last question for Joshua is the Roland framework publicly accessible? Can you talk whether Roland implementation is based on PyG? Is it available? How can people get access to it?
Mm-hmm. Yeah, so our work is currently in submission, so the code is not currently available, but we do implement the code using PyG and GraphGN. So I think in the near future, we'll open source all the code and feel free to use it.
Yeah. The code will be soon open sourced.
Yeah.
Yeah, thank you.
Thank
Great.
you.